Stanford University.
I have a few things I want to share with you, and it's actually a really exciting time, and I'm going to try to give you a sense as to why it's so exciting. This is not an average talk I'm going to give because we're at a special moment in history, actually, and I'll try to give you a flavor in the upcoming 30 or 40 minutes why this is such a special moment. And I thought I'd start a little bit historically. I'm going to talk about the search for Earth-like planets elsewhere in the universe, and then the prospects for life on those Earths. It's kind of neat to take a step back. Some of you are interested in history or Greek history, and it just so happens that Aristotle and the other great philosophers in the year 400 BC or so wrote extensively about the possibility that there might be other Earths in the universe and other planets that might have life on them. And Aristotle was very clear, and he wrote extensively about this. There's only one Earth. The Earth is at the center of the universe. There isn't life anywhere else. We're at a special place in the universe, and that's it. And it's obvious we're at the center of the universe because you look around and you see the sun and the moon and the stars and the planets. They all go around us. So we're clearly the center and special. Even then, there were Greek philosophers who disagreed with Aristotle. One of them was named Democritus, who invented the idea of atoms, and another one named Epicurus. And both of those lesser-known Greek philosophers said, no, there are many other Earths, maybe an infinitude of Earths elsewhere in the universe, and some of them have life, and civilizations come and die. So there was already a dispute, and by the way, those two lesser-known Greek philosophers were banished to the suburbs of Athens because of their crazy ideas, daring to disagree with Aristotle. And what's interesting is that here we are 2,400 years later, and we still don't know whether there are other Earths. There haven't been any other Earth-like planets discovered, no planets that have the size, the mass, the temperature, the environment of our Earth somewhere else in the universe. So actually, Aristotle's great debate literally rages on, and we scientists don't know whether there are other Earths. And so I'm going to give you a real scientific sense as to where we stand today and why I think we're at a special time. So to back up a little bit, one of the key questions, of course, is whether there are other habitable planets. And the quick answer to the question as to whether or not there might be other habitable planets is what I want to start talking about with just a few slides. And the first most exciting one you'll hear about all semester is that life got kick-started on the Earth, as far as we can tell from the fossil record, something like 4 billion years ago. So clearly, after a few blinks of an eye on the Earth, small microbial life forms started here on the Earth, which tells us that whatever the organic chemistry was that led to replicating molecules like DNA and RNA, and then eventually competed against other replicating molecules to become life as we know it, that organic chemistry process got started relatively early in the history of the Earth, and therefore that kind of chemistry might occur on another Earth-like planet, giving you some kind of optimism that life might be common in the universe. So that's one first step, and of course you might then invoke Darwinian evolution and imagine that Darwinian evolution leads inexorably to intelligent life. That's yet to be proven, by the way. Okay, so that's one step. Now, of course, right away, this conclusion has to be slowed down by virtue of the fact that we still only know of one example of life in the universe, namely here on Earth. Here in the year 2010, we have not yet detected any other life elsewhere in the universe, not even within our own solar system. So clearly we need more examples of life to find out how commonly it occurs and what the diversity of life might be. Is it always based on DNA? Does all life need water, or can it thrive on other liquids? Do other life forms evolve by Darwinian evolution toward intelligence, or are there other ways for life forms to survive? And of course, the search for life is one of the main activities of biologists, chemists, astronomers. Currently, we're surveying the planets and indeed the comets and the asteroids in our solar system, looking for signs of life either in the past as fossil forms or existing current life. And of course, among the destinations in the search for life are Mars, which is a Earth-sized planet, actually about a tenth the mass of the Earth, where there's clearly water on the surface. So during your lifetimes, you will hear of a sequence of NASA and ESA, the European equivalent, missions to Mars, hunting for signs of microbial life and maybe even more advanced life, especially in the aquifers beneath the surface of Mars. You all know the surface of Mars is dry and cold, but beneath the surface there's clearly some water. And so there's a chance there could be life there. And then Jupiter, although it's a big gas giant planet, hydrogen and helium gas, I don't think the chances of life on Jupiter are very high. But the moons of Jupiter, like Io and Europa, and you've heard of others, Callisto, Ganymede, those big moons could harbor life. And so there are going to be missions by NASA and ESA to Jupiter's moons, hunting for life on them, especially, again, beneath the surface. And then Saturn has extraordinary moons as well. Saturn is a beautiful planet with its exquisite jewelry, the rings, but it's the moons of Saturn that really have a hard, rocky surface, icy surface that could be an abode for life. So our solar system is a great destination to hunt for life, but let me tell you the bad news. I am 100% sure, well, okay, I can never say I'm 100% sure of anything, but 99-point-something% sure that there aren't other critters living in our solar system that have the intelligence and the technology of we humans. Our solar system has been scoured now with spacecraft. We have good pictures. There aren't great civilizations living on any of the planets or the moons. There aren't, resort hotels or golf courses or fancy technology anywhere. So our solar system is basically a non-starter when it comes to looking for intelligent life, technological life. So we really have to look elsewhere. And of course that means venturing outside of our solar system and into the Milky Way galaxy. And I just want to back up because I'm not sure how much astronomy all of you know. Our Milky Way galaxy consists of about 200 billion stars. All the stars you see at night are within our Milky Way. And here's a kind of a schematic. This is a different galaxy, but it's very much like our own. Spiral arms. Our Milky Way galaxy is 100,000 light years across. If you shine your flashlight at night, it takes 100,000 years for that beam from your flashlight to traverse the diameter of our Milky Way, even traveling at 186,000 miles per second, as light does. So our galaxy's enormous, 200 billion stars, and amazingly, the laws of physics and chemistry and math that you learned in high school apply everywhere within our Milky Way galaxy, and frankly, throughout the universe as a whole. So we can apply the laws of physics and chemistry and math, and even biology, maybe, that you've already learned to our entire galaxy, giving us some kind of a sense that the formation processes that led to the Earth and the other planets in our solar system, those physical processes might occur elsewhere, around other stars and their planetary systems, if they exist. So the laws of physics and chemistry being useful gives us, being universal, gives us a sense that we're not alone, that we're not special, unlike what Aristotle said. And in fact, if you look in our Milky Way galaxy with telescopes, you see big clouds of gas and dust. And on the right, you see the great Orion Nebula, which is the middle object in the sword hanging down from Orion's belt. And it's up in the night sky beautifully, by the way, at about 10 p.m. Just look out and you'll see Orion. There's his sword, obviously a sword. And there's the Orion Nebula hanging down from what is obviously his belt, if you've taken the right amount of illicit substances. So what's neat about the Orion Nebula, though, is in this big cloud of gas and dust are these very bright, and it turns out young stars, a mere 1 million years old. They are literally forming out of the gas and dust that's just floating through our Milky Way galaxy. And by gravity, the gas and dust congeals into stars. And if you look carefully at those young stars, here's what they look like. This is Orion again, the Orion Nebula. The young stars in Orion have these smudges silhouetted in front of the background nebulosity of the Orion Nebula. So there's the young star, and then this smudge of dark stuff is actually the gas and dust orbiting that young star, the placental material out of which the star itself formed a mere 1 million years ago. But it's this orbiting blob of material within which planets and the asteroids and the comets that we were just hearing about form. And so presumably in our own solar system, 4.6 billion years ago, there was a smudge of schmutz, of gas and dust around the young star, and planets, the ones we know and love here, formed, the asteroids and comets formed, and so on. And so we're seeing planets in the act of formation when we look at young stars, very obviously. So this again gives us some real hope and suggestion that planetary systems, maybe even like our own home solar system, are common in the universe. So planet building is probably, but we don't have real proof, planet building, like what happened in our solar system, is probably common elsewhere in the universe. Now, that leads to the main flow of my talk today, and that is, how would you then go about hunting for planets? And I'd like to ask you to take a deep breath here. Suppose one day you're at home and the phone rings and it's NASA, and they say to you, we would like you to engage in a project to hunt for planets elsewhere in the universe, and especially Earth-sized planets. And if you're talking to NASA on the phone, you have to start scratching your head and thinking, well, how would I hunt for Earth-like planets elsewhere in the universe? Somebody has to do it, and apparently they've asked you to do it. And that's sort of the situation we astronomers are in. We're trying to find methods out of thin air by which we could find Earths around other stars. And I've just named 3 obvious answers you could have given on the telephone to NASA. One is you might say, oh, well, point the Hubble Space Telescope and just see the planet around another star. That's a really good idea. Second one is, why don't you watch the star and see if it gets jerked around by a planet yanking on it gravitationally as the planet goes around the star. I'll talk about that in a few minutes. And then finally, you might think right there on the telephone, well, maybe you should just wait, watch stars and measure their brightnesses and wait to see if a planet crosses in front of a star, blocking some of the starlight, thereby dimming the star. So those are 3 pretty simple ideas, and I want to talk about each of the 3 of them. And these are real, honest proposals by which astronomers are hoping to discover planets, especially Earths, around other stars. So let me talk about the Hubble idea first, because that's such an obvious one. Point the Hubble at another star and look for the little dot of light that is the planet next to a nearby star. For example, the nearest star is Alpha Centauri. Why not point the Hubble at Alpha Centauri and look for little dots of light that are going around Alpha Centauri? Well, here is the situation. It's good to estimate, and I thought I'd give you a little bit of the math, estimate how bright an Earth might be around a star. And of course, planets, by definition, don't generate their own energy. They don't have nuclear, our Earth and Jupiter, they don't have nuclear reactions going on in the center like our sun does, powering it. And so planets shine by reflected light. Maybe they glow a little bit in the infrared due to the warmth. So you can work out how bright a planet might be. And I wanted to walk you through the math, if you don't mind. Here's a hypothetical star, and the light leaves the star spherically symmetrically, and some tiny fraction of that light hits the planet, shown there. And so you can then ask, well, okay, fine. A star has a certain luminosity. What fraction of a star's photons hit the planet and therefore might bounce off of the planet, reflect from the planet, allowing us to see it? Well, you can do the calculation. Here's the star. If you go out to the distance of the planet, there's an imaginary sphere whose area, as you all remember, has an equation 4 pi r squared. So the light from the star, the luminosity of the star, is being distributed over 4 pi r squared of area, and only a small fraction of that area, namely the cross-sectional area of the planet, if you took a knife and sliced that planet in half, it would have an area look like a circle from your vantage point on the star, and the area of a circle is pi r squared, where r now is the radius of the planet. So to recap, the fraction of the star's luminosity that hits the planet is the area of the planet, pi little r squared, divided by the area of the whole sphere over which the light from the star hits, and that's 4 pi capital R, where capital R, as you see, is the distance from the star to the planet. And you can then calculate that ratio, the fraction of the star's light that hits a planet. You can calculate that, let's say, for the Earth. What fraction of the sun's luminosity hits our Earth? Well, you can work through the numbers. We know the size of the Earth, the radius of it. We know how far the Earth is from the sun. You put those numbers in, and what you find is that the number is, sadly, pretty small. 10 to the minus 10. So that's 0.00000, I guess 9 zeros, and then a 1. So only 1 part in 10 billion of the light from the sun hits the Earth. Understandably, the Earth is actually pretty faint. If we were to observe our Earth from outer space, the Earth would be 1/10 as bright as the sun, and worse, the Earth and the sun are pretty close together as seen from somewhere far in space. So the angle between them is small, and so detecting the Earth at 1/10 the brightness of the sun is clearly going to be challenging at best. It's a little bit like trying to detect what do they call those? What are those bugs called in Virginia? Fireflies that light up, like trying to detect a firefly next to a searchlight. Very hard to do. And so I drew a little sketch of this. Here's a lighthouse, and of course lighthouses are very bright. And suppose there were a little firefly sitting on the struts here holding up that lighthouse. Would you know? 1/10 as bright as the lighthouse. So finding Earths is hard, and of course one way to try to find the Earths would be to somehow block out, turn off the light from the star, but we don't have any good way of doing that right now. We don't have great space-borne telescopes that can block out the light from a star, allowing us to see the planet nearby. So right now, we don't have the technology, even with Hubble, to detect Earths around nearby stars. And that's frankly going to be a major challenge in the upcoming 2-3 decades to build a space-borne telescope that can block the light from a star and let us see the Earth-like fireflies that are shining by reflected light next to them. So that leads me to the second method by which we can detect planets, and that's to watch, ironically, the star. They move, they wobble in response to the gravitational pull by the planet. So we can watch stars and see if they wobble in space. And let me give you a little physics intuition that I think all of you know, that, and if I could go backwards I would, but it's not important. The star obviously moves much less than the planet does, because the planet has very little mass yanking on this very massive star. So a little poodle on the end of a leash can hardly yank its owner around because the poodle has such less mass than the owner. And in this case, there's a way that the planet can pull on the star, and the leash is gravity. So the little poodle planet can barely yank on the star, and so it doesn't move much, and that's a matter of conservation of momentum. Mass of the star times velocity of the star is equal to the mass of the planet times velocity of the planet, and they orbit a common center of mass, like my hands are doing here. So as the star goes one way, the planet goes the other way, and so on. So that's the way it works. And of course, our sun behaves this way. Our sun, you were taught in elementary school, sits in space and the planets orbit the sun. Not true. Actually, while the sun holds the Earth in its orbit by gravity, the Earth tugs back on the sun gravitationally. And so our sun does a little Irish jig in space over the years. You see 1970 and 75 and 80 and 85 and 90 and 2025. Our sun is kind of getting jerked around, not just by the Earth, but by Jupiter and Saturn, Uranus, Neptune, and so on, all of them yanking on the sun. And you can kind of see, if you look carefully, there's about a 12-year duration for the sun to be jerked around once in this funny curlicue pattern. And that 12-year duration, 70, 75, where's 1980, there's 85. So it takes 12 or 15 years for the sun to make one loop. And that's because the big bully yanking on the sun is Jupiter, the biggest, the most massive of the planets in our solar system. So if you were to watch our sun from far away, you could infer the existence of not just Jupiter, but the other planets that cause the sun to do this drunken walk. Now, I forgot to say one thing about my talk, and that is that there's going to be some quizzes along the way. And we're getting close to some of the quizzes. But we're not there yet. The way we actually have attempted to find planets, and by the way, successfully, as I'll show you, is by watching for this wobble of the star in response to an unseen planet by using the Doppler effect. And all of you know about the Doppler effect. You've learned about it. I'll remind you that if you stand next to a train, even with your eyes closed, you can tell whether the train is a coming or a going by the change in the frequency of the sound waves, not the light waves, but the sound waves from the train. You hear when the train goes by. That's the Doppler effect, the sound waves being compressed as they slam into your ear, and then the sound waves being stretched out as the train recedes away from you. And the same effect occurs with light waves from a star. So here's a star. Half the time it's coming at your telescope. The other half of the time the star is going away from your telescope. And so you can see the light waves, not the sound waves, compressing and then stretching as the star comes at us and away from us. That's the Doppler effect. And so we can measure the change in the frequency of the light waves, telling us that a star is wobbling, which otherwise we wouldn't know. And a star shouldn't wobble. The only reason it would wobble, star in space, like the stars you see at night, the only reason it would wobble is if something is pulling on it, yanking on it, and that would be, of course, an unseen orbiting object, like a planet. So we watch for that effect, and now here does come that first quiz. I'll start you off easy. So here's your quiz question. Here's a star, there's a planet. They orbit a common center of mass. And so the question is, well, what is the question? At what point in the orbit of the planet, A, B, C, D, at what point in the orbit of the planet will the star's velocity be toward the Earth? There's the Earth. I'll let you think about it for 4 or 5 seconds. Where in the orbit of the planet will the star's velocity be toward the Earth? Okay, so I'll take a show of hands. How many want A? How many are too chicken to vote at all? Just tell me right up front. How many want B? 3 chickens. But no, 3 brave people. I'm sorry, I said it wrong. C, some hands. And then D, a few hands. That wasn't an overwhelming majority for any of the 4 of those. I'm wondering if I should give you more time to think about it. Well, I'll walk you through the answer, and then the next ones get a little bit trickier. So here's the planet going around. There's the arrow. And as the planet goes around, the star goes around too. And they always have to be opposite the center of mass. So here's the star on one side, like a teeter-totter. The planet's on the other side. And so if you think about it, the star's going around, the planet's going around. When the planet is here at D, going that away, the star will be here, going that away, toward the Earth. So I think the right answer is D. When the planet is here going that way, the star, which when the star's velocity pointing toward the Earth, will be over here. Does that make sense? So this is a basic physics that we'll use in a few minutes, and there'll be some more quiz questions that are at the springboard off of this idea. Okay, cool. Here's how the Doppler shift works. As a star wobbles around due to an unseen planet, and notice, indeed, the planet is unseen here. You don't see it, but it's yanking on the star. The star comes at us, the light waves are compressed, star goes away, the light waves are stretched, and that means that the colors of light, the wavelengths of light, change as we see them here on the Earth due to the star coming and a-going. And so you can imagine putting a prism at the back of a telescope and measuring those changes in color as a function of time, and thereby inferring the existence of the planet. And our sun, of course, does this. Here it is again. This is a hypothetical graph of the velocity of our sun over the course of time, 1960, 70, 80, 1990, 2000, 2010, 2020. Sorry, 2010, 2020. I've got to teach myself to say 2010, 2020. And you can see that the sun's velocity varies. And by the way, this is the velocity as seen from some distant star, like say Alpha Centauri, along the line of sight as measured by the Doppler effect. And so you see that the sun's velocity changes high, low, high, low, high, low, with a period of something like, well, as I mentioned, about 12 years, because that's how long it takes Jupiter, the big bully, to yank on the sun. And so if you lived at Alpha Centauri and measured the Doppler shift of the sun, you'd immediately infer, well, not immediately, it would take you 12 years, infer the existence of Jupiter, and you'd see that the amplitude of this wobble of the sun, notice that it's about 10 meters per second. That's due to the mass of Jupiter yanking on the sun. If Jupiter were twice as massive, the sun's velocity would be larger. And if Jupiter were less massive, the sun's velocity would be less. So you can infer not only the orbital period of Jupiter, but also the mass of Jupiter from this graph. Notice the daunting aspect, however, that I've glossed over. The sun, our actual sun, this is our sun, only moves by about 10 meters per second. That, of course, is Olympic sprinting speed. The Olympic sprinters run the 100-meter dash in about 9.3 seconds or so, 10 meters per second. So our sun is only moving at human running speed due to the biggest of the planets, Jupiter, yanking on. Of course, you can tell there's other planets in our solar system because this curve isn't very regular. Saturn, Uranus, Neptune, the Earth are yanking on the sun as well. Okay, so that's the idea. And of course, to do all of this, now if we're going to apply this technique to other stars, we need big telescopes. And we're using the work that my research group does uses the world's largest telescope, which is called the Keck Telescopes. The world's largest, there's two of them, Keck 1, Keck 2. They're located high atop a hopefully dormant volcano on the big island called Mauna Kea. And so you go there and you can use the Keck Telescope. The glorious part of the Keck Telescope is that there's a massive spectrometer about the size of this room with optics in it serving as a giant prism. The light comes in and comes in as white light, but due to the optics, the white light gets spread into all of its composite colors, blue, green, yellow, and red, spread like the colors of the rainbow, that we detect with a digital camera at the back. So here where the eyepiece would be, we remove the eyepiece, let the light stream through into the spectrometer. It's about a $10 million piece of optics, by the way. And when the light comes to a focus at a digital camera, we record it, as you can see here, I hope. I'm clicking, but I'm not getting anything. Please come in. See if that'll happen. Yeah, oh, thank you. That's nice. So this is what we see at the telescope. You see the full rainbow of colors. I won't go into great detail telling you how it all works, but suffice it to say that this spectrum shifts, Doppler shifts, as the star wiggles around. And you might want to try clicking on that once. So thank you. That shows you what the Doppler shift is like that. And now you can see that we have a little trouble because we have to measure very tiny Doppler shifts. So what we do is analyze this spectrum, this digital spectrum, on a computer. And the computer can actually sense when a spectral line, these dark lines, move a fraction of a pixel on the CCD, you can still sense it because the amount of light in neighboring pixels varies by a little itty-bitty amount that you can measure on the computer and sense movements of the spectral lines in the spectrum of a star by even 1/1000th of 1 pixel. So it's quite miraculous, and that allows us to detect very small planets. Let's see if I can click forward. Oh, good. Now, I want to show you some real-life data. This is a Sun-like star, 16 Cygni, and this is a graph of the velocity of the star 16 Cygni that we measured with the Doppler effect over the course of time, 1994 up to 2006. And you can see that early on, we made some measurements of the Doppler effect. That didn't tell us whether the star was wobbling or not, so we came back the next year. And the next year, the velocity of the star was different, as measured by this Doppler effect. That's a hint that the star might have a planet yanking on it. And so let me show you the next decade of data. Every dot represents a trip to the telescope. We open the shutter, we take a spectrum of 16 Cygni, measure its Doppler effect, and then go home. And you can connect the dots if you want and see very clearly that there's a periodicity. So let me now give you a quiz question, quiz number 2, I guess. Can you tell, just by looking with your eyes, what the orbital period of the planet must be that's yanking on this star? Yeah, there's a high point in the velocity, and then another high point about a little more than 2 years later, and then again, and then again. Every 2 or 2.5 years, the star completes one cycle because it's been yanked on by the planet that completed one cycle. So just by eye, you can immediately see this star has a planet that's yanking on it. And it takes 2.2 years to go around. Yeah?
Sorry, is it to answer the question?
Yeah.
Is it the velocity, like, relative to where we are, or is it, like, the absolute velocity?
Yeah, that's a really good question. And the answer is, I've cheated. The star has its own velocity zipping through the Milky Way galaxy. I've subtracted off that whole velocity. It's typically 30 kilometers per second. That's really fast, 20 miles a second. I've subtracted all of that off, and that's why you see 0 here right in the middle. Having subtracted, I've left you with just what counts, which is the change in velocity of the star due to the planet that's yanking on it. So you can immediately see that the planet, whatever it is, takes 2.2 years. And by the way, let's put this in relative to our Earth, which of course takes 1 year to orbit the sun. So here's a planet that takes more than twice as long to orbit its star as the Earth does to orbit the sun. So it must be farther away from its star than the Earth is from the sun. And there's something called Kepler's third law, which I won't talk about, that allows you to calculate precisely how far away the planet is from the star given the orbital period of the planet around that star. So that's pretty cool. We know how far the planet is from the star. And I mentioned something earlier that now I'm coming back to. The amount of wobble of the star is due to the massiveness of the planet. The more massive the planet is, the more strongly it can yank on the star. So this amount of wobble, there's something called a semi-amplitude, the amount of velocity up and the amount of velocity down. Notice that it's about 50 meters per second. Tells you that this is a pretty massive planet, more massive than our own Jupiter that, remember, kicked around the sun by only 10 meters a second, the Olympic running speed, just a second. And so here you can see this 50 meters a second, and now I've drawn in the computer simulation of what a planet being something more massive than Jupiter would cause this star to do. And it comes out from the computer that this is a planet 70% more massive than our own Jupiter, orbiting in 2.2 years around this particular star. Yeah?
But since it would be both the distance from the star and its size that would affect how much pull it has, how do you separate the two?
Brilliant question, beautiful. And the answer is This star, like most of the stars that, let's say, you can see in the night sky, have already been categorized. We've measured their masses, and you're absolutely right. Let me just repeat her question. You really do need to know the mass of the star to know how violently it will be jerked gravitationally by the planet. And so we have a pretty good estimate of the mass of the star. It's about like the sun, by the way. So you do need to know the mass of the star in order to take the orbital period and convert it into a distance, as you said.
Yeah. What affects the shape of the curve?
You know, there's one question I haven't addressed yet, and that is what affects the shape of the curve here? And the answer is it should have been a sine wave like nearly the sun showed, but it's not a sine wave. It's more like shark's teeth. The velocity of the star ambles up slowly, and then the star gets jerked down, and then the star changes its velocity. When then the star's jerked down to lower velocity, that tells you right away that the orbit of the planet cannot be a circular orbit, because then you'd get a smooth variation in the velocity of the star. But instead, the planet's orbit must be elongated, elliptical, eccentric. And so we can build a computer model, as I've shown with the dashed line. Let's see if I can, I know I can move forward here. Yeah, there we go. Oh, sorry. Before I show you about that, I have another quiz question. Sorry. And here it is, before I tell you the answer to the shark's tooth shape. This, I think, is easier, but maybe I'm wrong. So this is just a little math quiz to make sure you're on board. Here's hypothetical velocity variation for a star over the course of time. You see the hypothetical data points. And so quiz question number 1 is, what is the orbital period of the planet? What's the period of this sine wave? And you can see the scale on the bottom, the x-axis, 0 to 200 days. So I'll give you a few seconds to think about what's the period of the sine wave here. All right, well, let me give you a shot at it. A, B, C, 1 or 2 hands, and D. Uh-oh. D wins. I think it's 30 also. If you go look at one peak, the next peak is about 30 days later, roughly. Maybe 20. I can't tell by eye, but maybe it's 28 or something like that. So this is a 30-day period. What about the semi-amplitude? Question number 2. Semi-amplitude of this sine wave. It's got a vertical axis, 0, minus 20, minus 40, 0, plus 20, plus 40 meters per second. This is the velocity of the star. So is the semi-amplitude 1, 3, 10, or 35 meters per second? Well, I think I won't even go through the trouble. I think it's pretty obviously nearly 35 meters a second, because the velocity goes up 35 and then down 35 and so on. So that again tells you the mass of the planet. Okay, that's cool. Now let's get to this shark's tooth thing. So remember where we were. I showed you this plot of the velocity of the star 16 Cygni, and remember that the velocities have this odd, non-uniform, non-sinusoidal shape. And so the question is, why, oh, why is that? Clearly the orbit is eccentric. So you build a computer model simulating the effect of such a planet on the star. And here's the computer model. There's the star, there's the planet. You see, when the planet is close to the star, notice how the planet gets whipped around the star. And then here's the, it doesn't actually make that sound. And then here's velocity versus time from the computer. You can see the computer can predict, hypothetically, from just physics, what the velocity of the star should be as a result of this planet. And notice the star's velocity gets jerked downward when the planet is close to the star. And so we have a model that predicts a velocity that agrees within the errors with the measurements. And so that's a great example of a model that allows us to infer the properties of a system based on the observations of that system. So this is a pretty cool way to use computers to make progress. Here's what the orbit looks like, as you guessed. There's the star 16 Cygni, and here's the planet going yung, 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 like that. And for reference, here's Mercury, Venus, Earth, Mars, just shown to give you a scale. Remember we said the period was 2.2 years. Indeed, this planet orbits beyond that of Mars because that's what the 2.2 years is telling you. It takes a long time for the planet to go around the star. Now, does this planet maybe harbor life? Could it be a habitable planet? I doubt it, and I'll be blunt and quick. This planet being 70% more massive than Jupiter is probably made of hydrogen and helium gas like our own Jupiter. Maybe it's a big ball of iron and nickel and silicates, but probably it's hydrogen and helium. Why? Because the dominant constituents of our universe as a whole are hydrogen and helium gases. So when you make something massive like a star or even a large planet, probably they're made of the dominant constituents of the universe, namely hydrogen and helium. So the best guess, and it is only a guess, is that these big fat Jupiters are nothing more than big balls of hydrogen and helium gas. Would they be habitable? Probably not, because a big ball of gas, if you had, critters on the surface of that planet, they would sink in to the depths of the planet. Of course, you can't be too quick, and I've been too blunt and a little too given it too short shrift because, of course, while life might be unlikely on the planet, such a large planet might well have moons, and this artist's rendering suggests the possibility of a moon, and that being the case, you could ask, could the moon be habitable? And some people ask about floating critters on the planet, and then the moon itself having water, allowing there to be life on it. Let's see if I can click forward. Please click me forward. There we go. So some people speculate about moons so massive that they might actually retain their liquid water, rendering the moons Earth-like, albeit satellites of their host planet. Oh, there was a quiz that just went by. Yeah, go ahead.
I'd just like to confirm that with radial velocity measurements, you actually, it could be like a bored cube going around a star. You don't really know it's here.
I get in the mail every week letters from kindergartners, first and second graders, and they render their own artistic sense of what the planets look like that we've been discovering. And many times the kids render the planets as cubes or pentagons, and then there are beings that live on these cubes. And you're quite right, we don't know whether the planets are cubical. Of course, they're almost certainly not. The interesting thing is that the third graders are unanimous about what food the aliens like to eat on those other planets. Pepperoni pizza. Time and time and time again, it's always pepperoni pizza. Incredible thing. So now we got this is the hardest. Oh yeah, go ahead.
How do you,
Ask more questions because this is the hardest quiz question.
okay. How do you know that the change in velocity isn't being caused by multiple planets?
Yeah, that's a good question, and sometimes they are. We've detected some stars that have 2, 3, 4, and in one case 5 planets. And here's what we see. If there's just one planet, the star wobbles around in a nice smooth way. If there's 2 planets, we see the star wobble around but superimposed on yet another wobble. And then if there's 3 planets, we can decompose very much like closing your eyes and having your friend play 3 notes on the piano. You can tell it's 3 frequencies hitting your eardrum even without seeing how many fingers have hit the piano. And we similarly analyze the frequencies coming from the motion of the star. Okay, this quiz question is the hard. Go ahead.
Greg have something on his website to play with the different.
Yeah, there are some websites, one by Greg Laughlin and others. You can actually make up planetary systems, dream up planetary systems, and then let the computer program predict the velocity of the star due to those multiple planets. So you can.
Out the website.
Yeah. Okay, this is the hardest quiz question. I'm actually going to give you. I'm going to give you a whole minute, and I'm going to shut up because this is a hard one. Here is a graph of the velocity of a star over the course of time, only 20 days. Very simple. Velocity over the course of time. And you see it's just a sine wave. What could be easier? A sine wave. And I've marked the points A, B, C, and D. So A is when the velocity of the star, remember, that's all we measure, is 0. And then B, the velocity is high. C, it's back to 0. And D, it's low. And here's the background information. From the Doppler measurements, a star exhibits a sine wave variation in velocity, as you see. The orbital plane is edge-on to the Earth, just like my hand, causing the planet to block the starlight. Every once in a while, the planet will cross in front of the star, dimming the star. We're going to talk about this more in a few minutes. So here's the question. At what point on this velocity plot, A, B, C, or D, do you think the planet will go behind? Oh yeah. At what point on the velocity plot will the planet go not in front of, but behind the star? And I'll just give you a necessary piece of information before you panic, because this isn't that easy, but it's not hard. By convention, astronomers use positive velocities, like point B, to mean that the star is moving away from the Earth. So as we measure the velocity of the star minute after minute, year after year, month after month, so on, when the velocity of the star is away from the Earth, away from you, we call that a positive velocity. And then by converse, when the velocity of the star is negative, that means the star is coming at you. So I'm going to give you 60 seconds to think about this. At what point in this velocity plot, A, B, C, or D, will the planet be going directly behind the star? I'll give you a minute. And you can talk amongst yourselves, by the way. It's better to talk about amongst yourselves, as a matter of fact.
So, give it to me. Probably the hardest question in the room. Not because the velocity relative to the story as means. It's actually moving the fastest away. And when it's the fastest away, the stars in front of it. I mean, the planet's in front of it. It's heading towards the front.
If it's moving the fast opposite of speed, that means actually
Because the planet's the
here, the
opposite.
sun's over here.
Right? So when it's done doing that, wouldn't the planet be in front? Would you want the planet to be behind? There's like triple dyslexia going on here. It's pure, yeah. No, but then the star would be accelerating towards you at that moment. It's like there's 3 invariants when it's reading it out. You start with the sun. At C, the sun has stopped moving away. That's correct. It's just stopped moving away. So it stops moving away. Isn't the sun planet in front of it? We want the planet to be behind it. Well, it has to be A or C because it's when the star has been moving towards you. The star has been moving towards you, right? And the planet's being propelled behind it.
All right. Let's take a vote. Let's be democratic. So let's go through the letters again. How many want A? A bunch of people want A. How many want B? How many want C? A bunch of people want C. And how many want D? A few people want D too. Well, let me talk through it myself because I don't know the answer, so I have to figure it out. I don't even know where to start, so I'm just going to start at B because the velocity is high there, and I said that by convention, positive velocities mean the star is moving away. So I'm going to use my hands because I don't know what else to do. I'm going to let this be the star. Here, let's let this be the star. If at point B, up there, the star is moving away, that means the planet is coming toward us because whatever direction the star is going, the planet must be going the other way. So that's where you are at point B. A quarter of a cycle later, a quarter of a period later, the planet is in front of the star. That's C. A quarter of a period later, that's point D. And that brings you back to point A, where the planet is behind the star. I think I talked my way through that. I hope I didn't fool myself. I might want to do it a second time to be sure I got the right answer, but I'm emboldened by the fact that so many of you voted for A, so maybe I'm right, but I would want to do it again. But I think it's A, and you can see this is a little bit of it's a remarkably simple question, but it's sort of geometrically challenging to kind of work it all out. All right, so let's go on. I want to now introduce you to my favorite planetary system in the whole universe, Upsilon Andromedae. And you can see it in the night sky. It's up right overhead this time of year. And here's how you find this star. If you want to see my favorite star in the night sky, it's visible to the naked eye. What you do is you drive in your car to the Andromeda galaxy, turn left, you go a little ways, a few hundred light years or so, actually a few million light years, and you run into this star, Upsilon Andromedae. And you can pick it out amongst all the other bright stars nearby because it's the one with the little turquoise arrow pointing right at it like that. So that's the way you find it. And here are the data. What a mess. Velocity versus time. It looks like somebody threw the data points on the graph without even thinking. But if you look more carefully, you see that they tend down, then up, then down, then kind of up, down. There's something not random about these data points. And so you can analyze them. Frankly, we use Fourier Analysis. But there's an easier way, and that is to zoom in on a little tiny section. And when you zoom in, you see this. And immediately you can follow the data points. They go up and then down and then up and down. You can connect them all with a sine wave. Here's a nice continuous stream of the measured Doppler effect. And you can see remarkably that this planet goes around its star in only 4.6 days. This is a planet going around, take 1 year for this planet is just a mere 4.6 Earth days. So it's a very close-in planet. We can measure its mass, as you know now. It turns out to be 60% of the mass of Jupiter. And that's not the end of the story, because if we then subtract the effect of that planet from the original velocity measurements, you still have left over the star wobbling. And you can see very clearly that there are two periodicities still in the data. There's one that takes about 2/3 of a year, up and down. And then there's another periodicity down and up and down and up, taking about 3.5 or 4 years. So there are yet two other planets besides the one. And this, of course, answers your question. Here you see clearly how 3 planets emerge. And of course, we know a lot about these planets. Here's the civil engineer's sketch of the system. There's the star Upsilon Andromedae. The closest one, the middle one, the outer one. We know their masses, of course. The outer one, 4 Jupiter masses from the measurements. The middle one is twice the mass of Jupiter. And the inner one, as I think I've already mentioned, is 60% of the mass of Jupiter. And sadly, we don't have names for any of them. It's kind of pathetic. I got a letter in the mail a few years ago from a girl. Let me try to remind myself. She was in 7th grade in Idaho. And she says in her letter, "Dear Professor Marcy, I heard about your discovery of 3 planets around a star." She says, "I don't know if you've named your planets, but I have suggestions for you." And so I'm reading her letter, you know, thinking, oh boy, here, whatever, this is going to be crazy. She says, "Okay, here's my idea." She says, "I think you should name the outer one Forpiter." Very good. She said, "I think you should name the middle one Tupiter." And then she said, "I think you should name the inner one Dinky." So we don't have names for any of the other planets. Those are the only ones for which we have names. Oh, by the way, I should here. Can you go back? I got another postal mail, not email, but postal mail from a guy. I open up the letter and he says, "Dear Professor Marcy, I'm a retired math professor, and I've come up with a mathematical proof that there's no intelligent life around the innermost planet of Upsilon Andromedae." I'm thinking, oh man, I get a lot of crank letters, by the way. So this is another one, obviously. A mathematical proof that there's no intelligent life around that inner planet. He says, "Here's my proof. What intelligent species would want to pay income taxes every 4.6 days?" Now. So this slide is indeed about a year old. We found about 100 planets. There's a team in Switzerland doing great work. some other teams at Harvard and other places doing great work. And among all of us, we found another 100 planets this year. So we're up to like 400. Here's a histogram of their masses. I think I should skip this slide other than to say, this shows you how many planets we've found as a function of their mass. And notice we haven't found any that are 1 Earth mass. Found planets that are 100 times the mass of the Earth and 1,000 times the mass of the Earth, even 10 times the mass of the Earth, but not one. And so we're still missing this holy grail of planets that are like the Earth. So I want to now turn my attention to the third method of finding planets, which I would like to propose to you is the most likely way, not just in your lifetime, but during your tenure as a Stanford student, you will hear about the discovery of the first Earth-sized planets ever. And here's how it works. As I hinted, the way it works is by looking for the dimming of stars as an Earth crosses in front of those stars, blocking a small fraction of the starlight. And we've just launched, we meaning NASA, have just launched a new telescope in space. You may or may not have heard about it. Maybe you did it in passing. The Kepler Telescope. And it successfully launched just 9 months ago. I was there in Florida. It was spectacular, tears streaming down my eyes as this telescope launched successfully and didn't go splashing down in the Atlantic. Here's a little technical detail. Forget this slide if you'd like. There's what the telescope looks like. It's just 1 meter in diameter, so it's a medium-sized telescope, but it's in space, like the Hubble. So that makes it great. It's got a big digital camera, 42 CCDs, something like, I've forgotten, about a gigapixel set of CCD imaging capability at the back end. Does it say how many pixels? No, it doesn't. But it's something in the realm of 1 billion pixels. So it's a big old camera at the back. And we're going to be working on this for 3.5 years. I'm one of the investigators in this program, so we're working very hard. I want to show you the launch.
6, 5, 4, 3, 2, engine start, 1, 0, and liftoff of the Delta II rocket with Kepler on a search for planets in some way like our own.
Fourier engine chamber pressures are building. Grounded solid motors are building chamber pressure. Increasing at this time. Pressure's looking good.
Solid rocket boosters.
1 seconds into the flight. Recovering from the initial launch transients. Guessing 34 seconds. Mach 1. Vehicle's now going supersonic. But motor chamber pressure is beginning to trail off as we're passing 45 seconds. Engine chamber pressure, good steady state value. Symmetrical burn on the grounded solids. Coming up 55 seconds. Standing by for burnout. Burning out of the solids. And for separation. You see separation? And we have ignition of the air-lit solid motors. Air-lit solid motors building in chamber pressure.
So it was quite a moment. I can tell you, I was watching from the beach right outside Cape Kennedy, and people had, their tears were streaming down their faces. They were screaming. It sounded like a giant orgy. It was unbelievable. I can't even begin to describe to you how happy all of the Kepler scientists and engineers were there. And we'd been working on this for a decade, and to see it actually go up successfully was really quite a moment. And here's how it works. Very simple. As an Earth crosses in front of a star, it blocks a fraction, 1/10,000th of the surface of the star, causing the star to dim by the blocking of the light, like a fly landing on a light bulb. And so the star's brightness declines and then rises back up. And it better happen again regularly. Every time the planet goes around, you should see the dimming again and again and again. So there's a prediction that has to be met by further observations, which is a succession at exactly the same time interval of the dimming of the star. Yeah.
I was just wondering, in terms of how long it is dimmed, like the fraction of time that it is dimmed, are you able to find out the mass of that planet and of the star, or does it matter because it's the ratios?
You've really touched on an interesting question. We can't measure the mass of the planet at all, but we can measure directly the diameter or the radius, because the bigger the planet in size, not mass, but size, the more light from the star it blocks.
So you know the stars. Okay.
Yeah, and that's a very good point. Similar to the other question about the mass of the star, we also know the radii, the sizes of the stars. So that's a good thing. We know the size of the stars. So you're quite right. Your intuition is perfect. We only literally measure the ratio of the area of the planet, pi r squared, to the area of the star, pi capital R squared. But we know the radius of the star, so we then can solve for the radius of the planet.
Yeah, is there an issue where, let's say, the plane of orbit is perpendicular to the...
We see zippo, nothing. Yeah, in fact, it's much worse than that. You've touched on an embarrassing point, thank you very much, which is we only detect those planets which, by luck, reside in an orbital plane, like a flat piece of paper, that's right along our line of sight between the Earth and the star. All of the other tilts, 20 degrees, 40 degrees, 70 degrees, we don't see any of those planets. So we're only detecting a tiny fraction of the Earth's, but this is by far the best way to detect Earth, so you got to go with whatever you can do. Oh, darn. Can you go back? Just real quickly, the Kepler Telescope is pointed toward the constellation Cygnus, beautiful constellation in the sky near Lyra, and there are the 42 CCDs that are at the back of the Kepler Telescope watching those 150,000 stars minute after minute after minute, measuring the brightness. That's all it does, is measure the brightness of 150,000 light bulbs out there in the Cygnus constellation, looking to see if any of them dims in a periodic way due to the planets. So it's quite a simple experiment. And now I want to show you some of the actual data. This is hot off the press. I couldn't have shown this to you a week and a half ago. We just announced these planets on January 4th. Is that Monday? Was January 4th a Monday? Oh yeah, because you had to be here. Sorry. So on January 4th, we were all in Washington, D.C. We made a big announcement, and we announced 5 planets, the first 5 planets discovered by Kepler. And I want to show you the data because they're just exquisite. Here's a graph of the brightness of the star that we call Kepler 17 over the course of 45 days. So these are days along here. There's 45 days. And if you look carefully, you see that the star had a certain brightness. We normalized it to 1.0, and then the star dimmed, and then dimmed again, and then dimmed again, then dimmed again, and so on. You could comb your hair with these data. And if you fold all of these data points on top of each other, you get this one dimming, which is the sum of all of these. Look at how beautifully mapped out the dimming of that star is every time the planet crosses in front. How much does the star dim? 1%. Goes down to 0.99, and look at the exquisite precision. Literally, about 100th of 1%. And that's the goal of Kepler, is to be able to measure the brightnesses of stars to within 1% of 1%. In other words, a part in 10,000. So we're doing that. This, it turns out, is a Jupiter-sized planet. There it is, 1.27 times the radius of Jupiter. We know the orbital period. Every 3.234 days, you get this dimming. So we know a lot about this Jupiter. We know its size, as you can see. Here's another one, Kepler 8. Here again, you can see the dimming. By the way, here's where the telescope was turned off briefly to transmit the data back to Earth, because Kepler's way out there, about 1 million miles away. So we have to take a break, send the data back to Earth with radio waves, and then go back to taking data. Here they are folded together. Beautiful thing. This is another Jupiter. But of course the question arises, what's the mass of this planet? How do we know the mass? Well, that's where the Keck Telescope comes in again. So we go back to Keck, and this is one of the things that I spend a lot of my time doing. We go back to Hawaii, and now we try to measure the Doppler shift of the star's light in order to deduce the mass of the planet. We already know its radius from the amount of dimming, And so we actually can get the mass right away. In addition, and this is the trickiest thing I'm going to tell you today, in addition, we see another effect. This is so complicated, I'm almost apologetic for telling you about it, but hang with me here. This is a graph of the velocity of the star measured by the Doppler effect over the course of time, I called it orbital phase, during about 2 hours. And what's happening here is amazing. Suppose here's the star. Stars actually spin on their axes. And so as the planet crosses in front of the star, it blocks the approaching part of the star that would have given a Doppler shift, but now you're blocking that part of the star that's coming at you. And then as the star continues on, it then blocks the part of the star that's going away from you. And so there's a net Doppler shift due to the fact that the planet first blocks the approaching half of the star, or a portion of it, and then the planet blocks the receding portion of the star. And that's what's seen here. The velocity jumps up and then comes down and then goes back on its merry way. This gives us a chance, it's amazing, to detect what direction the planet is going compared to the direction that the star is spinning. If the planet had gone around the star the other way, then we would have seen a drop in velocity and then an increase. So we can actually compare, to use the physics lingo, we can compare the angular momentum of the planet's orbit to the angular momentum of the star's spin. Those two vectors can be compared and measured. And this shows that they're aligned. The planet's going around the star in the same direction that the star is spinning. And that's maybe what you would have guessed if you think about how planets form in that early placental protoplanetary disk era. So that's pretty cool stuff. Here's what the planet looks like. It actually, we can tell from these data that the planet crosses the star, yes, dimming it, but actually slanting at an angle, giving those funny data that I just showed you. It's actually called the Rossiter-McLaughlin effect, if anybody cares. And now here's my favorite of the Kepler 5 planets, and I'm going to spend a couple minutes on this one because this is the best. This star, Kepler 4, yes, it dims periodically. Check it out. Dim, 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 dim. But look at how much this star is dimming. It only goes down to 0.999 of the original 1.0000. So this star is only dimming by a part in 1,000 of its original brightness. That tells you immediately, just by your intuition, that it's a small planet. It's blocking only 1/1000th of the area of the star. And so we can tell that its radius is small. It's only 4.1 times the radius of the Earth. And I just take a break here and take a deep breath. The goal of Kepler is to find Earths. And I told you that maybe during your Stanford tenure, you might be here while Kepler discovers the first ever Earths found. And you can see that a planet that's 4 times the size of the Earth stands out like a sore thumb. So planets that are equal to the size of the Earth will similarly stand out. They'll be a smaller signal, but certainly detectable. So we are very encouraged by this detection of a planet 4 times the size of the Earth, because it's so obvious in the data. Here it is standing out easily. Yeah?
I was just wondering, in the case of finding a planet the size of Earth, wouldn't it also definitely matter in terms of the orbital, like how close it is to the star?
Yeah, well, you mean for which aspect of it?
For thinking about life on that planet.
For life on it?
Yeah.
Oh, well, you've hit a home run. I mean, the truth is, and I'll give you the details, the truth is this planet takes 3.2 days to go around its star. That tells you the planet's very close. Clearly this poor planet is going to be blowtorched by that nearby star. You know, if you lived on that planet, the temperature would be, I can tell you, about 1,500 degrees Celsius. Unsuitable for the survival of organic molecules, never mind, you know, our human bodies and multicellular life as we know it. You could cook a chicken in a millisecond, except there wouldn't be any chickens on such a planet. So these are not habitable planets. And I'm not going to spend any time on this because you're going to get plenty of it during the rest of the semester. But clearly, the kind of Earth-like planets that would be habitable must be farther from their host star to have an equilibrium temperature more like what we enjoy here on the Earth so that organic molecules can survive.
So are you hoping to find more of those in the appropriate range as the telescope is up there for longer,
Well,
so you have a longer period?
You're making the hairs stand up on the back of my neck. It's exactly right. And you may have noticed in one of my previous slides that Kepler is supposed to last for 3.5 years. That's by design. Because in 3.5 years, a true Earth analog, a clone of the Earth, will take 3 years to cross in front of the star at least 3 times. And then that'll give us 3 dimmings, dim, 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 every year another dimming, confirming the existence of the planet. Once you see 2 dimmings, you can predict when that third one ought to occur if it really is an Earth orbiting the star. And seeing that third one, will be cheering. So 3.5 years is, as you say, long enough to see a planet that takes 1 year, like our Earth, orbit its star. Is there another question?
This has been frustrating me. How do you know when you're measuring the wobble whether that system is on the plane towards it? Because in this case you do finally, but all the others it could be wobbling like this.
Yeah, so there's a cup half full and half empty. In these systems where we see the dimming, we know unambiguously that the orbital plane is edge on. And so the full wobble of the star away from us and toward us is what we measure with the Doppler effect. But in general, when we don't see this transiting effect, this dimming effect, you're right. We don't know whether the orbital plane is inclined 20 degrees, 40 degrees, 60 degrees, so we have no way of knowing. And that tilt diminishes the Doppler effect that we see. And indeed, with a face-on orbit, there's no Doppler effect at all. Yeah, because the star doesn't come at us.
Same thing with the density. Because you have the diameter for the first time, you can take the weight. Otherwise, you're just making up gas or rock or anything.
That's exactly where I'm heading. And I only have a few more slides that I think I want to talk about. Here are indeed the Doppler measurements for that Kepler star. Kepler 4, remember, it's got 4 times the radius of the Earth. I went to Keck. Here are the Doppler measurements. This is messy, but I'll clean it up for you. Here's velocity measured by the Doppler effect. Here's time. This is June 1st of last year. I know because I was there at the telescope. Very exciting. And then this is the rest of 2009. We just finished in December last month. And here are the data points. You can't see if you squint. The points actually sit fairly close to the predicted velocity variation of the star based on the dimming. But let me now fold it for you so you can see it. So now here's velocity, and here I've folded all of the orbits into just one orbit. Here's one orbit, and here's the next orbit. And you can see the velocities go up and come down and go up. It's a little non-sinusoidal, so you already know the orbit is not perfectly circular. But clearly, the velocities vary just as we predicted, and so we know the mass of the planet. It comes out to be 20 times the mass of the Earth, 20 Earth masses. So we know the radius of the planet, and we know the mass of the planet, 4 Earth radii, 20 Earth masses, and now you can do the math. If you know the mass of a planet, and you know the radius of the planet, the radius tells you the volume, 4/3 pi r cubed. Mass divided by volume tells you the density. So we actually can determine the density of the planet. This is, by the way, a circular orbit fit to the same data. It could be a circular orbit, but probably not. And what's neat is we can determine the density. We use the Greek letter rho for density, 1.9 grams per cubic centimeter for this planet. Now, let's think about this, because this is the most exciting aspect of the Kepler mission and why it's so powerful. We now know for the first time the densities of these planets. And you know something about densities, because when you were in high school and you took chemistry, you know that the density of water is 1 gram per cubic centimeter. This is a planet more dense than water. It's obviously denser than gas, hydrogen and helium, and it's even more dense than water. But it's not as dense as the Earth, because the Earth has a density of 5 grams per cubic centimeter. Take the mass of the Earth, divide by its volume. So this is a planet denser than water, but not as dense as the Earth. And that leads astronomers to concoct, and maybe that's the right word, plausible interior structures for this planet that Kepler found, Kepler-4. And this is a sketch showing the range of plausible interior structures. Probably this planet has both rock and water. That's the only way you can get a density of 1.9. Can't be just water and gas, and it can't be just rock, like the Earth. So we've proposed that it has iron and nickel in the core, like the Earth, a silicate mantle, like the Earth, and then you have to add water in large amounts in order to make the density lower than the Earth's density of 5 grams per cubic centimeter. And maybe, but we don't know, there's an envelope of atmosphere, gases, hydrogen, helium, maybe carbon monoxide, carbon dioxide, ammonia, who knows. So we don't know about the atmosphere. But we are very sure that there has to be roughly equal admixtures of rock and water to give us this intermediate density. It's a very exciting moment because for the first time we're detecting planets whose interior structure we can guess, and they have water, almost certainly. And of course water is a key prerequisite for life as we know it. And so we're getting the first hints of other worlds that might harbor this solvent critical to organic chemistry. And I think I might want to stop here with maybe one more slide. Let me see what my next one is. Yeah, this is a summary of the Kepler results. Here are the 5 planets we announced. Kepler-4, remember, is the teeny 4 Earth radius one, so that's maybe the most exciting. And I'm going to stop here, I think, except to just say one last thing, that with Kepler, in the next, well, 3 years, because there's 3 more years of the mission, we are very likely to detect the dimming of stars from Earth's. We should be able to determine their radius, their mass, and hence their density, and we'll be able to report to you whether that density is 5 grams per cubic centimeter, i.e. the density of Earth, making it a rock. And maybe we'll be able to ascertain the temperature of that Earth by virtue of its distance from the star, telling you whether the water would be in liquid form or frozen into ice or evaporated into steam. So we should be able to find Earths, verify that they're rocky planets, and ascertain their effective temperatures, their approximate temperatures that would render them possibly habitable. I think I'm going to stop there, and that way I can take questions. Yeah.
On this.
That was an asteroid that hit the Earth that caused that to happen. It was not me.
On the slide with the smallest one that Kepler discovered.
Yeah, Kepler-4.
The variations were only 0.1% of the light.
Right.
And
1/10 of 1%. That's right. Yeah.
And so even then, it looked like there was a lot of noise.
Yeah.
Along just the normal sunlight without the dimming there.
Right.
And if that's 4 Earth radiuses, something that's 1 Earth radius would be like 1/16, right?
Bang on. You're exactly right.
So are you going to detect just a dimming of? Will you actually be able to detect that 100?
Yeah, it's a lovely question, and you've characterized the challenge exactly correctly. That the noise was, significant. You could see with your eye. The dimmings were quite large compared to the noise, but now 1/16 of that signal, would you detect it? Not immediately easy, but remember, every time that Earth crosses in front of the star, you get another slight dimming and another slight dimming, so you can add up all of those dimmings, and the noise will begin to average out, and so you'll get a more and more accurate reading of that dimming. So you're right, it's a close call. I'll give you the numbers just to tell you how it works. We can measure the brightnesses of stars to about 20, let's see, how am I going to say this? 20 parts per million. So I said 1 part in 10,000, but actually we do about 5 times better than that. And an Earth blocks 1/10,000th of the light. So actually our errors are 1/5 of the dimming signal. So it's a close call. You know, the signal's just going to be 5 times deeper, that is to say the dimming will be 5 times larger than the errors. So it's you know, if finding Earths were easy, we would have done it a long time ago. Yeah.
How did you choose the initial area of the sky? Is it just
this is a really funny question. Question, if you didn't hear it, how did we choose the Cygnus constellation? And the reason we chose Cygnus is we knew that only a few planets would be residing in these edge-on orbits so that they would cross in front of the stars. So we need a lot of stars. And as I said, we're monitoring 150,000 stars. And that's the critical need. How do you have a telescope monitor 150,000 stars? You point it at a place where there's a lot of stars. And you can see in a picture of our galaxy, it's in the plane, in the flattened plane of our galaxy, where there are a lot of stars. So Cygnus is the constellation Cygnus happens to be oriented near the plane of our galaxy, and so that's why we chose it. There's another place in the southern hemisphere where the galaxy crosses, and we could have chosen the southern hemisphere, but the world's largest telescope, the Keck in Hawaii, is, of course, in the northern hemisphere. So we chose the north so that we would be able to use that Keck telescope to follow up and get the masses and the densities of the planets. Yeah.
I'm curious, so you said the mission, Kepler, is going to be 3.5 years?
Yeah.
Total?
Yeah.
So then, I'll speak pessimistic, but let's say you're not able to find a planet that is common to ours with the same density and same mass and same radius.
Right,
Then
right.
What steps is NASA NASA going to take from them?
Well, let me recast your question a little bit differently, because it's a really good one. We don't know whether Earth-like planets are common or rare. Surely there's some elsewhere in the universe, but maybe they're 1 in a million. Maybe Earth-sized planets are really quite rare, and our solar system is a weirdo. That's possible. And if so, after 3.5 years, we will have announced 0 Earths, and we will be able to say we would have detected Earths had they been there, but we didn't see any, therefore Earths are very rare, and we'll be able to put a quantification on how rare they are. That'll be a real bummer, and it'll be, you know, as bad a hair day as you'd have when an asteroid hits. You'll have a much worse hair day when we don't find any planets like the Earth, because then Congress is not going to be very likely to fund NASA's next generation mission to hunt for Earths. So there's this kind of, I'm giving you a political answer. If we don't find any Earths, it's going to put a damper on the hunt for habitable planets in the next decade. On the other side of the coin, if we do find a few Earths, I think members of Congress are going to be tripping over themselves to vote another, $500 million or something for the next NASA mission to do this. And actually, I just lied. It's going to be $3 billion. Yeah.
I just wanted to follow that up. If, say that the first year, like you didn't catch a planet on that first year, would it be possible to not confirm, like even if you saw 2, to not confirm the third one?
Yeah, it's always possible that you see a dimming, and then you see another dimming, but one or both of them are spurious. Maybe it's just a confluence of noise, that just happened to be less noise, or maybe a speck of dust, interstellar dust from one of those damn asteroids, one of those, what were they called? Meteoroids, floats in front of the Kepler Telescope, blocking the light from the Kepler Telescope because of this stupid speck of dust. Floats in front of the Kepler Telescope, so you see 2 dimmings.
For more, please visit us at stanford.edu.